Welcome to Lecture 2.7, Change of Bases. In the previous lecture, we learned how a linear map T from X to U is encoded by a matrix with respect to an input basis for X and an output basis for U. It is natural to ask how changing the basis changes the matrix. In this lecture, we will answer this question. In the special case of T being from a matrix to itself, that is an endomorphism, we will see that two matrices, notice in this case they will be square, A and B, can represent the same linear map if they are similar. That is, if A equals P, B, P inverse for some invertible matrix P. We'll see why this is the case, and I will actually show you how to construct such a P explicitly. And this is called a change of basis matrix. Okay, let's get started. Let T be a linear map from X to U, and x1 up to xn be a basis for X, and u1 up to um be a basis for U. Remember that X is isomorphic to k to the n and U to k to the m. And henceforth, I'm just going to use R in place of K, although it really doesn't matter. Any other field would work. So what this means is that we have isomorphisms. Let me write this down. So we have isomorphisms. We have one, it's called a B from X to R to the N, and C from U to R to the M. Now, since we already have chosen our bases, let's just assume that B sends xi to ei, and U sends ui to ei. And of course, ei is just our standard unit basis vector with zeros everywhere and a 1 in the ith entry. Okay, now what we can do is we can put these isomorphisms together to get a linear map from Rn to Rm. And I think this is easiest to show you with a diagram. So we start with this linear map T from X to U. And now we have isomorphisms. We have B that goes from X to Rn, and C that goes from X to Rm. So now this map right here is just the result of doing B inverse, then T, then C. So I'll write that as B inverse, then T, then C. Now there's a special case of this, which is quite common, is when X and U are the same. In this case, we can take the input and output basis to be the same. So EI is UI, and we assume that B and C are the same. And then we get a matrix, M, which is B, T, B inverse. So I want to say that M and T are similar as linear maps, although we're going to look at what this means in terms of matrices. So let's continue this example, but let's assume that X and U are the same. So let me, I'm going to redraw this diagram to the right. So I will, so T goes from X to X. B goes from X to Rn. C goes from X, sorry, this is also B, forgot that. So B goes from X to Rn again. And now this matrix here, this is M, which is B, T, B inverse. And remember, we are reading as function composition right to left, B inverse, T, B. Okay, so now let's suppose that we have a different isomorphism. Instead of B, we'll pick another one called, let's call it C. So let me write that over here. So let's suppose we change the isomorphism B. And let's let A from X to Rn be another one. Let me show you how I will add this to the diagram. So let's start off from here at Rn, and let's go back to X. So I'm going to write B inverse here. I mean, we could go up here, but I think it's going to be more apparent if I do this. It'll be less cluttered as well. So now this map is T. Notice that this is the identity map, T, and the identity map. And now let's do A. So we have this new isomorphism. And one way to think about this is that it sends a different basis to, or it's basic. When I say different isomorphism, it just means that we're basically picking a different basis. So suppose we have a different basis, yi, that we send to ei, and we have a vi that we send to ei. Although we have already said that ui and vi are the same. So in this case, we are, instead of using xi, I guess we're using yi. Okay, so let's continue on with this map. So let's draw A from X to Rn, and A from X to Rn. And now, this map here, let me do this in blue now. Let's call this N. Now, N, you can think of as A, T, A inverse, but I also want to highlight Rn. So now we have a commutative diagram. Let me add a map here. So this map here, let me call this S, which is A B inverse. This map here is S equals A B inverse. So now this diagram, let me highlight this. Okay, so here, 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 and here. And now we are entirely in Rn. So M and N are similar matrices because they describe the same mapping of a vector space to itself, but with a different choice of bases. One of them with this choice, the xi's, the other one with the yi's. So let me write that right down. So similar matrices describe the same mapping of a space to itself, but using a different basis. Now, these are obviously different mappings of X to itself. So I'm not saying that this is the same map as this, but I'm saying that they both represent this linear map with the different bases. And actually, we will see how these two things, I'll show you an example in the next slide, it'll be easy to generalize, how these things do actually represent the same linear, they can represent the same linear map if we are careful from Rn to Rn of how we choose our bases. So think about X as just an abstract vector space. Maybe it is a vector space of functions or a vector space of polynomials. It's something that's maybe not in the most convenient form to work with, and moving over to the N allows us to use the very useful framework of matrices that we can do a lot of things with. So that's really why we want to do this. So we want to turn our problems of studying vector space, finite dimensional spaces, into studying matrices. And one question is, how do these similar matrices, how are they related? How are the corresponding matrices related that come from different bases? And here's an answer. Let's finish with an example, and we'll do one in R2 that I really like. I think you'll find this to be very illustrative. So T is a linear map from R2 to R2. And let's let A be the 2 by 2 matrix with respect to the standard basis E1 and E2. Let's see what the matrix of T is with respect to a different basis. Let's say two vectors V1 and V2 that are AC and BD. So here's how we're going to start. So we will start down here from R2. And our old basis, let me draw this here. So this is E1 and this is E2. And here's R2 over here. Now this basis, what color do I want to use? Let's use blue here. So this basis over here determines a grid. In other words, the basis determines a coordinate system. And if we use the standard basis, it determines the standard grid. Well, it's just a square grid. Now let's apply the matrix A to get over here. Now the A is some matrix, I don't know what, let's say it's like alpha, beta, gamma, and delta. And the columns of A are the images of E1 and E2. So let's say that E1 gets sent up here. So this is T E1. And let's say that E2 gets sent over here. So this is T E2. Now this determines a completely different grid. And this is, well, let me draw this first. It's hard to draw and talk. Okay. And we're going to look at the same picture in the next section when we talk about determinants. Because the determinant, I don't know if you learned this in your undergrad class, is a scaling factor. So if this 1 unit of area here turned into, what is this, 6 units of area over here, that's the determinant. It's the scaling factor, up to sign. Okay, so now this is one way to think about a linear map. I like it. You're literally picking these guys up and you're moving this one up over here and this one over here, and you get this grid. Now that said, another way to think about this is without the grids. Imagine that you take the same picture and remove the grids and color different points in R2 a different color. So you got a red point, a green point, a cyan point, a yellow point. You have all these colorful points in R2. Then when you apply A, I should say when you apply the linear mapping T, because now we don't have any basis here, these points get warped. So maybe there's a, well, let's see how many, I don't know how many colors I have here. So this green point gets sent to that green point. This this purple point gets sent to, let's see, this is 2 of these and 1 of these, so 2 of these and 1 of these. So that purple point gets sent to this purple point. And this yellow point, this is 1, 2, gets sent to 1, 2, so that's going to be somewhere over here. So imagine T just takes these points and warps the points. It doesn't matter what grid is on top of it. The grid gives us a way to count steps in certain directions, but the linear map is just the colors moving. Okay, so let's now, so A is this matrix. Let's understand how this matrix is different, would be different if we use the different basis. So what we're going to do is we're going to draw the same picture of R2 up here. So, so I still have a yellow point here. I still have a purple point here. I still have a green point right here, etc. But we're going to pick a different basis. So for this basis, I'm going to pick. Let's see, what color do I want to use? Let's say that V1, say this is V1. You know what? I'll use use purple because my grid below is in blue. So I'm going to use, so let's say this is V1, And let's say V2 is something like this. So we have V1 and V2. So let me take note of this. Down here we have our old standard basis, E1 and E2. And up here we have our new basis, V1 and V2. Okay, so let's figure out what matrix, actually let's call it P, is going to change this new basis into our old standard basis. So we actually want to go from our new basis to our old basis. So let me write down how this works. This is something that we learned in the previous lecture. So if we're going to go from here to here, this is going to be our input basis, that's going to be our output basis. So let's take, I'll say, input basis, V1, V2, output basis, E1 and E2. So this is what we learned in the previous lecture. We take V1 and V2 and we apply P to it. So up here, these are our basis vectors. So this is like 1, 0, and this is 0, 1 in that coordinate system. But when we move down here with our standard basis, V, let me actually draw it down here. So V becomes AC, and this is V1, and V2 becomes BD. So V1 is AE1 plus CE2, and BD is BE1 plus DE2. So up here, PV1, in this, our standard basis, we can write as AE1 plus CE2 and P applied to V2. So this gets sent to, so this is just the identity map, but it's with respect to a different input and output basis. So this sends V2 to BE1 plus DE2. So this P is called a change of basis matrix. It really is the identity map, but it changes what the basis is. And remember how we construct it, the columns, these rows are the columns of the matrix. So P equals A, B, C, D. So again, it's the identity map, but it changes basis. So now we're up here. We're R2, and we are ignoring the coordinate system. It's easy to get confused. Just focus on the dots. And let's apply the map T. So I said A, but really this is the map, the linear map T. Both of these are the linear map T. Just in matrix form, it's this, and we'll figure out what the matrix form is up here. And again, think of this as ignore the grid, ignore the basis. You just send these colorful dots to the corresponding places over here. So again, this is the yellow one goes here, the green one goes here, and the purple one goes here. Forget about the actual lines. So what's the matrix with respect to this new basis? Well, similarly, if we go over here and we apply P, that sends it, so all that does is that sends us from here down to here, and the identity map on here, and changes the basis. So in other words, this map that we want to do can be constructed in 3 steps. So starting up here, do the change of basis matrix to send us down here, then apply the matrix A to send us over here, and then do P to send us up to here. So remember that diagram we had on the previous slide. So let me do it in miniature over here. So R2 to R2. So let's call this B. So this is B. This is P. This is R2. R2, this is A, this is P. So we conclude that in our new basis, P is equal to, so let's see, P is equal to, or B is equal to P, A, P inverse. So so that is P, A, P inverse. So equivalently, we could write that A equals P, B, P inverse. And the moral of the story is that P is the change of basis matrix where the columns of P are the coordinates of our new basis with respect to our old basis. Okay, so that's the end of the section on linear maps. And so please keep sticking around and we will learn about k-linear maps and determinants in the next section.